So I would like to very briefly, very fast go through basics of fuzzy logic, and to make it feasible, that you will get at least some rough idea on how it works, what are the principles. Let me do this lecture. Let me wrap this lecture around an example, a very simple example. I can see that some of you are writing something, so I have no idea what is it is on. Is there any other message? So that I'm unable to check it right now. So please be patient. Yeah, let's. I'm not going to respond to any questions related to the test because we are very short in time. Actually, what I'm going to do to present you fuzzy logic in 45 minutes or 40 minutes is a task probably similar to learning to get a neurosurgeon over the weekend, but we will try. So let's imagine that we have the following situation. Let's imagine that we have a car and that we would like to build an algorithm that will be trying to provide keeping the right distance behind some preceding car. So basically, I would like to consider the problem of creating an algorithm for active cruise control. This is something that is present in several. Right now, this is offered in many brands offer this functionality. And so to define this functionality, I would like to build an algorithm that is trying to provide me with a safe distance, and it should appropriately respond to all possible events that can happen. And these events are I'm accelerating, or the car in front of me is accelerating, or it is slowing down, etc., etc. So how can we solve this problem? The first way of solving this problem is I would call it analytically. What I can do is I can try to describe analytically the problem. We have a mass, we have some power of the engine, and we can try to build a system or a single differential equation, and we can try to solve this problem. The problem with this proposal, with this way of solving it is that, first of all, it is complex. It will be a complex procedure because I will need to solve a differential equation, and numerical solutions are never very fast. But the more important problem is that I miss exact data, because if I would like to be analytically correct, I need to know exactly what are the physical properties of the problem that I'm describing. And I will miss this data. That's inevitable. So the second way of solving this problem is to try to follow something that drivers do. And this something is just the common sense. A driver is not calculating anything. At least it is not solving in his mind differential equations. Instead, driver is using a set of very simple and common sense rules. And let's assume that we are using two possible facts that are necessary to draw a conclusion. So the facts or observations that I will be using in solving the problem. So these are observations this is something that we will pay attention to. It will be a distance. It means how far do I have to this preceding car, and what is a difference in velocity. So I will just use delta velocity. What's the difference in velocity between my car and the car that is in front of me? And based on these observations, and basically that's all the data that I need to behave in a reasonable way, to take appropriate decisions. What decisions will I take, and what analysis does a driver do? So this analysis can be stated in a form of extremely simple rules. So the first rule that I could say that I will present you is, for example, if I am close and I'm faster, then it's a good idea to slow down. So basically, this is how do we solve this problem. We are following such a very simple common sense rules, and these common sense rules are expressed in a natural language. So the first observation that is necessary to do is that I am mixing natural language. So these are natural language expressions. Natural language expressions, or we are using basically words which has some very vague meaning, because the meaning of the term close is not very well defined. It is something quite subjective, and it's quite inconcrete. Also, faster. What does it mean, faster? Again, this is inconcrete. This is not very specific. So I'm mixing here words, and I'm mixing here some logical operators, some logical expressions or operators, expressions. So to wrap up this, this mixture of logical analysis and words, in concrete words, is just something that developed into a fuzzy logic. Fuzzy means that the terms that I'm using, my variables, because I can say that the words that I'm using are variables. So I can say these are two variables, and this is also some variable. So these words are variables, and I'm trying to manipulate these variables using logical expressions. And basically, this is fuzzy logic. Variables are inconcrete. They are fuzzy. They provide me very inspecific description of the world. These variables are often called, in a little bit more fancy way, as linguistic variables. So words, you can find the term for naming these words as linguistic variables. So that's an introduction. We are talking about reasoning with words, and we will be trying to make these predictions or make this analysis in it will be at the heart of our system. And this heart of our system will be something that I can name fuzzy inference module or fuzzy inference block of some data or information processing system or algorithm. This will be this algorithm will be enclosed inside this box with dashed borders. And the system is supposed to convert some observations. So I will have some observations, and these observations will be provided, will be delivered by different measurement devices that my system will be using for making these inferences. Because in my car, what I will need to enable this functionality of active cruise control, I will need a radar. I will need a radar module. This radar module will be just sending a beacon to the front, and this wave will get reflected, and my appropriate software of my radar device will be converting this into two or more pieces of data. So for example, I can estimate how far is an obstacle, so a distance. Also, it's very easy to compute what is a relative difference in velocities. Yes, because the velocity is just a distance over time, and the relative velocity is just a difference between my car and the car that is in front of me, and I can calculate this using this radar acquired data. And these observations will be something that I will be feeding to my algorithm. So I will have variables that are specific. So distance, so this distance, I will just once again, distance d, and this differential velocity or this difference in velocities, they are both very specific values. So I will tell that these are variables with very specific concrete values. So I will say these are crisp variables. And these crisp variables will be an input to my algorithm. So I will be having here a particular numbers. Let's say it will be 50 meters. I know that the car is 50 meters away, and I know that I am, let's say, 10 kilometers per hour faster. And this will be inputs to my algorithm. As I said, I could use this data probably to solve differential equations and appropriately plug them so that I hopefully could determine what to do. But I'm going to do it in a very different way. I will be doing this using these rules, these rules that are using linguistic variables, and these rules that use linguistic variables I will name fuzzy rules. So this expression, if I am close and I'm driving faster, then I should slow down, is a fuzzy rule. And you can formulate several common sense fuzzy rules. And the list of these rules will be short because we actually don't need to consider very many different situations. We can just consider that that distance can be expressed by a subset of words that that are sufficient from the point of view of our reasoning. And these words are, for example, I'm close, or I'm far, or I'm at the right distance. So basically, these three values of this linguistic variable distance are sufficient to implement common sense rules. And the same is with this relative velocity. Here I can have either that I'm faster, I could drive faster, I could drive slower, and let's say the same velocity, or relative difference is maybe instead of same, it's better to say it's zero. Let's keep it same. So I can say that this is a domain. This is a domain of my fuzzy rules. I will be using these linguistic variables as arguments to my fuzzy reasoning. What I have at the input, I will have crisp variables. What I would like my system to produce, it should produce something that implements the right reaction. This right reaction actually is described in my rules, again, using some linguistic variables. Slow down is one possible outcome of the analysis. Speed up is another one. And probably the last one will be no operation, don't do anything. So my fuzzy rules will be using these linguistic variables, distance and relative velocity. So these are arguments. So these arguments I will plug as input to my fuzzy inference. At the same time, at the output of my fuzzy inference, I will be producing information that is expressed with, again, linguistic variables. But what I need to produce, what my algorithm is expected to produce, it is expected to produce something very concrete, because if I would like to implement this system, it should work on its own. So it will be given, it will be fed with observations taken from radar, and it needs to appropriately control the velocity of my vehicle. So let's assume that the way we are doing this, that we have an electric car. So at the output, I will have a voltage. And this voltage, if it is positive, then it means probably to accelerate. If it is negative, probably slows down, slows the vehicle down. Around zero means it does nothing. So we have a processing path. So these blue and green arrows are just to indicate that I will have linguistic variables at the input and at the output. So these arrows were just to show you that I will be producing something based on fuzzy inference that uses linguistic variables and produces linguistic variables. But the flow of operation in my system will be the following. I will be given here this crisp data. So this crisp data, I will have to convert into these linguistic variables. So there will be two different concepts, distance and relative velocity. And within a concept distance. I will have three different terms, three different linguistic variables, and the same within a concept relative velocity. And I will be, what I need to do if I would like to implement this fuzzy inference, I have to convert input CRISP variables into all these possible linguistic variables. So basically, if I would like to be exact, there should be 6 different outputs here. So let's make inside, instead of this dots, there are just 6 outputs. There will be 3 outputs grouped for a distance, for expression in natural language, expressing different concepts related to a distance. And there will be 3 lines that are used to express concepts related to a differential velocity. And I will need a block that will be providing this conversion. So I will be converting information about measurement of a distance, and I will be converting this information related to a measurement of a relative velocity, and this will be done by a block that I will label with a letter F, and this letter F stands for a fuzzifier. This is a funny name for a module that is trying, so this is this F, for a module that will be converting observations onto linguistic variables. And again, here, I will have another block, and the task of this block will be to tell me exactly what to do, or to generate an exact value of a voltage. Voltage is something that I'm interested in. And this needs to be based on one of the 3 possible categories output categories that I listed here. And this block, so I will have the opposite operation here. From a set of linguistic variables, I will be trying to produce a single value, a crisp value. And this block will be called a defuzzifier. So this is something that inverts the operation of the first block. So it's not very legible, so let me write again, or draw again, a structure of a fuzzy logic system. It will be composed of a fuzzifier, and the heart of this will be this fuzzy logic inference block. And once I perform this inference, I will defuzzify, and I will have crisp values at the input and crisp value at the output. And processing, the analysis of data will be done in this fuzzy logic inference block. So how can it be done? You will see that it is extremely simple. Everything is extremely simple. So let's begin with the first part, the part that transforms observations onto concepts. I told you that I need to make a conversion, for example, from a distance that is a crisp variable, that's just a distance in meters or in any other unit, and I would like to convert it to one of three different linguistic concepts. The first one is close. The second is right distance, and the last is far. So I would like to make this conversion. And how fuzzy logic does it? It introduces, and this is one of the most important concepts, it introduces something that is called a membership function. A function just because it is used to convert between a domain. Here, a domain is crisp, and a result will be a concept. This is a fuzzy domain. So this is something that transforms from data from a crisp domain to a fuzzy domain. And this membership function is just a recipe that tells us how do we convert a crisp observation into a level of satisfaction of either of these concepts, because we will be assigning each concept. So I will be assigning each concept, close, right, far. I will be assigning with something that I could tell a level of satisfaction, or how this concept is satisfied in given a particular observation. So this is what I would like to do. And then if I know how valid is a concept, I will be trying to see how valid my rules are. So I can say that the flow of my processing will be the following. First, see how valid are concepts. If I will have this information, then I can tell how valid or how important are rules, are these fuzzy rules that I have just defined. Just to give you an example, if I am, let's say, 1 kilometer away of a car that is in front of me. So basically, I can say that probably it fits extremely well to a category I'm far. And so it fits well, but close, I don't think this is close. And also right is not the category that I would opt for. So if I have a rule that says if I am close and I am faster, then do something. Then do something. In this case, this rule would say then slow down. But the premise, arguments to this rule are not valid if my observation is 1 kilometer. So if they are not valid, that means that this rule shouldn't be activated. The consequence of this rule, or the conclusion of this rule, is something that I shouldn't really pay attention to, because it just doesn't fit to the data I have. And formally, I could say that I will be evaluating how valid is this rule, or validity of the rule. I will be trying to or rule validity of a rule. I will be trying to evaluate it, and I will tell that this validity is measured with a rule activation. That's another term that I will be using. Rule activation or activation level. This will be something that is another term to tell how important this rule is, or how active this rule gets. So the membership function, I hope you understand the flow. I will be trying to assign every concept a level of its validity for a particular observation. There will be different observation, there will be different validity of different concepts. And these concepts, like far and faster, are used in formulating rules. So a rule will have a premise. So this will be a premise of the rule, or my observations, and the rule will have a conclusion or a consequent. So every rule will have a consequent and will have a premise. And I will be measuring the premise, how valid or how active is this premise, and it will imply how active the consequent should be, how important the consequent should be. So this is a premise, this is a consequent. And now let's be more specific, and let's go to these membership functions. So these membership functions are the way of assigning validity to different concepts based on some functional form, and let's assume that we are talking about this distance. So we will be having a crisp observations in meters, and let's assume that I will have here particular values. So let's say this, I'm 50 meters away, I'm 100 meters away, and here is 200 meters away, and so forth. And now I will have this membership function. Membership function will is customary denoted with a mu letter, and this mu letter will take as an argument this distance. Oh yes, this lecture will be available. I'm recording this. So here is this membership function, this mu, and this mu will have a particular value for a particular concept, or a particular shape for a particular concept. So if my concept is, for example, I'm talking about a distance, so let's say I'm talking about the concept close. So I can say, okay, I define a membership function mu c, and it will be operating on a distance. And I can say that the membership means that the membership is something that tells me how well a crisp observation fits my concept. So how well this observation fits the concept that I'm interested in. And I need to have some range of this fitness. And the reasonable range of fitness is from 0 through 1. So I can say that this will be this fitness measure. So I can say that something fits completely, very well, or ideally, my concept, and I will assign it this observation with a value of 1. And if it doesn't fit at all, I can tell it's 0. It doesn't fit at all. And this is the convention that has been adopted. Obviously, fuzzy logic is something that is extremely flexible. So you can experiment with a variety of different ideas on how to assign values of membership to in different cases, to different variables. But the most commonly used approach is that we will be building a function that converts some domain variable like distance onto, it will be mapping on of an interval between 0 and 1. So if I would like to draw such a function, and again, the function is drawn by an expert in a field. So now let's assume that I'm an expert in a field, and I'm saying, okay, up to, let's say, 25 meters, I could tell that I'm any distance up to 25 meters, in my opinion, means that I'm close to my preceding car. And let's forget right now that obviously it depends on the velocity. Let's don't make things too complicated. But assume that up to 25 meters, I'm saying that this will be the maximum value of this membership function. Let me put this limit not in green, but in black. This is the maximum limit of my membership function, and my concept clause that I'm here denoting in green. Let's make this like this, for example. Let's make the function that is piecewise linear. It is composed of two segments, and let's say that it ends at 100. So I can say that let's say this is 100. So I may say I'm an expert, and I think that up to 100 meters away, I can say that something is close. Maybe for one person, something that is 50 meters away is no close any longer, but for some other person, it might be close. And observe that I'm assigning a membership function, let's say, for example, to this 50 meters. The membership function 0.5. So that's the way of translating crisp observation onto a very fuzzy concept. I can now consider another category, like far. So let's assume that black is blue is far, and I can draw. Well, let's say that the far I can define like this, for example. This is far. Let's assume that everything that is up to over 150 meters ahead is for sure is clearly far. That's I can say that, okay, let's assign it 1, the membership 1. If something is closer than that, maybe I'm hesitating whether it is a good way to name it far, but it is justified because for some it could be far. And the last thing, let's assume that I have this category, right distance, the correct distance. And let's assume that this correct distance I can model using triangular function. So I chose to use two different shapes of functions. The one is triangular, the second is trapezoid. And these are very frequently used functions as membership functions. But again, here you are free to choose any shape that you wish, that you think is reasonable. So now, how this conversion would be made? Assume that I am observing velocity, the distance, and let's assume that it is, let's say, 60 meters. So if it is 60 meters, I can look up the membership functions and tell that, okay, 60 meters means that my concept close is valid, but not fully valid. And 60 meters probably less than half. So let's say that it is valid to the 0.4 level. So it is okay. I can say it is not impossible that I can treat it as a close. It's not very well fitting this category though. I can say the same now far. According to my functions that I have just drawn, the far 60 meters is not far. So I assign it with 0. And the last category, the right category that I just introduced, is a category where I could say, okay, this is, let's say 0.2. So look that my falsifier was a block that was fed with a crisp observation and produced 3 different results for 3 different concepts. So for close, I produced 0.4. For far, I produced 0, and for right, I produced 0.2. And as you see, this fuzzy and similar functions I can define obviously for the second concept. So these were the functions. These were the membership functions that correspond to concepts. This is close, and this is this will be far. So this is far, and the last one is right. So this is right. And exactly the same idea can be applied to converting relative velocity onto 3 different values, onto 3 different concepts. We are basically, we should be finishing, but if you don't mind, I will take you 15 more minutes. So that we could advance a little bit and you will have a better understanding of the problem. So I apologize, but today is a special, we have a special situation. And this is our last lecture, our last meeting. So let me take you a little bit more time. So the membership function I can apply now to converting my relative velocity, and this will be again these will be membership functions, and among these linguistic variables that correspond to relative velocity, I identified 3 different concepts or 3 different categories. So the first was faster. The second, again, this will be in blue. Slower, let's make it green, and let's make this orange to be same. And now I need to be more specific. And what are relative velocities? So here is 0 relative velocity. And let's assume that this is, let's say, 10 kilometers per hour. So let's assume that it is in kilometers per hour. So here I'm 20 kilometers faster, or I can be slower. So domain here also goes into negative values. So again, as an expert, I can propose some shape for the membership functions. Again, the maximum value of this membership function here is 1, and the minimum is 0. So the concept same could be defined this way. The concept faster could be defined, for example, that way. So let's can start with 5, and here we can do something like this. And similarly, I can define a concept slower this way, and this is a job for an expert. So if I get observation, let's say that I'm, for example, let's say 6 kilometers per hour faster than a car ahead, I can translate this into 3 different validity levels of these concepts. So the concept faster will be assigned a value of something like 0.2. A concept same will be assigned a concept 0.4, and a concept slower will be assigned with a value 0. So I hope it is clear. So to combine both elements that I have just proposed you for this particular observation, I'm getting 2 inputs. So this is what I get from my sensors, from devices, from measurement devices, and I'm outputting 6 different values, and these are grouped in 2 bunches or 2 groups. And for a distance, we have close, we have far, we have right. And for relative velocity, we have faster, and we have slower, and we have say. So slower SL, and here is say. And what do I have is I have assigned a validity to my linguistic variables. So now I can try to think what rules could be formulated for these linguistic variables that will be helpful in terms of taking decisions. What are the rules? Basically, I can tell I have 3 different variables related to a distance, 3 different variables related to a relative velocity. So I can say that I might formulate 9 different rules that combine both concepts related to a distance and the concepts related to a relative velocity. So these rules will have different premises, will have different situations that they analyze. So let's enumerate this. So I've just erased this 9 because it is not that it's not that important message. And let's just enumerate these rules. So the first rule will be if I'm close and I'm faster. So let's assume that this is this distance-related variables, and here are in the second column will be different velocity-related variables. So that will be the first rule. The second will be if I'm close and I'm slower, if I'm close and I am at the same relative velocity. Now the next 3 will involve if I am far and I'm faster, I'm far and I'm slower, and I'm far and I am same. And 3 more rules if I am at the right distance and I'm faster, if I'm at the right distance and I'm slower, and the last rule is if I'm at the right distance and I have the same velocity, I'm not going to type to write it anywhere else. And these are rules these are premises of my rules, and I can tell that my rules that I will be using, again, that they should be designed by an expert. So this will be if-else rules, and an expert's job is to say what to do. So if I'm close and I'm driving faster, then I have this first possible conclusion or consequent: slow down. If I'm close and I am driving slower, what would you propose as an action, taking into account the three actions that I identified? I identified slow down, speed up, or no operation or not. Yeah, the same. So let's use this no operation, no change. Now I'm close and I am driving slower. What would be a possible reaction? Okay, again, I'm an expert, and I might wonder whether isn't it a little bit risky strategy. I'm close, I am slower. Okay, that's okay. Strategy is okay. I am here, I am close, I am slower, so I'm at the same speed, so I think that the better is to slow down. That's a better choice, because I'm close, the same speed, that might cost me a problem, a trouble. Okay, next three rules. If I am far and I'm driving faster, what to do? My choice would be don't do anything, don't change anything. If I'm far but I'm faster, I will get there in a while. So I don't need to accelerate. If I'm far and I'm slower, here obviously speed up or accelerate. This is a reasonable choice, and so forth and so forth. So I hope you get the idea. And these are common sense rules. This is something that should be intuitive. And obviously, for some of you, it might not be the right rule, and this is okay, because you will be experts that will be designing this kind of algorithms, and if your understanding of a problem is erroneous, then probably the whole algorithm will work erroneously. But what is important here is that I defined different rules. And I also told you before that these rules should be as valid as their premises are. So if a premise, I'm close and I'm faster, is really valid, then this will be an important rule. But if this is not the case, it should not be an important rule. So how can I evaluate how valid is a rule or how valid is a premise? A premise, as you see, is a Boolean expression. So the point is that I would like to evaluate validity of a rule. And the rule, so evaluate rule validity. And the rule validity I'm evaluating through evaluation of its premise validity. How valid is its premise? And the premise, that in all of these rules, these premises were extremely simple. They have a form A and B, where A and B were linguistic variables. These variables were unlike in logic. In logic, we have rule AND in logic. But this rule AND expects its arguments to be binary. That means 0 or 1. That's what admits a regular logic. But now our variables are continuous. They are continuous values within a range from 0 to 1. But if you think a little, it's the logic is something that is trying to idealize a common life, the world. It's simplifying this world, and the world is not that black and white or 0 or 1. Yet the logic works even if it is not black and white, because we are making decisions all the time based on variables that are not necessarily binary. They are rarely binary. So I can say that this logic AND is something that is a special case of some more general rule. And the general rule that is used for combining the variables so that we can get as a result an evaluation, a reasonable evaluation of how they in conjunction, what is their conjunctive output or conjunctive result is something that is called the product rule. And is a special case of I'm sorry, this is not a product rule. So just forget it. This is a product rule, will be in a while as a special case. And this is what I want to introduce, is something that is called a T-norm. This is some generalization of logical AND. And this T-norm has several specific ideas on how to implement it. And one of them is a product, for example. Because you can say that logical AND is a product, like in algebra. 0 times 1 is 0, 0 times 0 is 0, 1 times 1 is 1. But if I look at this as a product, observe that now I can use arguments that are non-binary. Continuous arguments are legal for this kind of operation. But there is another T-norm that is commonly used in fuzzy logic, and this is a min rule. Min rule, it just selects the minimum of the two. So this will be this fuzzy AND operation, this fuzzy AND operation. So I can say that I can evaluate expressions, my fuzzy rules, by just performing extremely simple operation on variables. So if I have a variable, if my close variable is 0.2 and my I'm faster variable is let's say 0.4, I can say that the result of this is the minimum of the two, is 0.2, and so forth. Okay, look, it was impossible, just like learning how to do a surgery over a weekend is impossible. So it was impossible to conclude a lecture on fuzzy logic within 40 minutes. I have a proposal, and just feel free to accept it or not. We can meet next week for a lecture that will conclude this fuzzy logic. So if you wish to do that, if you wish to do so, we can meet at 3 next week. If you cannot do that, because I am aware that you might have other subjects, then it is okay. And you will have this also during lab work with Mr. Piotr Łuczak. And you already have this background that you are in the middle of it. We are in the midway. So what is left is not that much. So I might ask Mr. Łuczak to explain you what is remaining, what is still to be presented. So I would like you to maybe not to vote right now, but you just could make a decision in your group and send me information, let's say by Monday, whether you are interested or you don't have time and you cannot afford it. And basically this is what I would like to tell you, and I would like to conclude here at this point. So thank you for your attention. I will be expecting your answer. I hope there is one person who is who can represent the group. I hope you can. Yeah, let's make a poll, and if depending on the outcome, we either meet next week or not. Okay, thank you for your attention once again, and have a nice day and the remaining part of the week. Okay, bye-bye.